Okay, welcome to the next online lecture. This is on section 1.2. Um, I'm going to try to keep track of the time here and try to be about 10 minutes, but let's see what time is it now. Okay, so let's see how this is going to work. First off, last time we talked about what a differential equation is. So we all know what a differential equation is. Excuse me. I need a little coffee. A solution to a differential equation, or a differential equation itself, is just really an expression that has the function and its derivatives. So what is a solution to the differential equation? A solution is a function that if you put it into the differential equation, if you put the function into the differential equation, you get a true statement. So the solution is the unknown function, right, that the differential equation has. Good, and so DEs are used in mathematical models, and last time we saw several mathematical models that we used. And finally, last time we solved y prime equals ay plus b. And so today what we want to try to do is to look at graphical interpretations of the differential equation. So that's typical in a mathematics course. An object can be looked at algebraically, which is what we did last time. We algebraically looked at the differential equation, and it can also be looked at graphically. So what is a differential equation? So here's an example before we get too far into it. I just wanted to review a little bit about the algebraic version. Do you remember how to solve this? If we have ay plus b, the solution is c e to the at minus b, or minus b over a. And so if we just look at this, we get this is c e to the at minus b over a. Good. And so now one question comes up often in differential equations. If you have a solution, what is its long-term behavior? And here you see that the long-term behavior of this solution, no matter what the choice of c is, the exponential part of this function is going to go to 0 because of the negative 2. And then we're just going to be left with 5/2. So in this case, the long-term behavior of this solution is that the y of t always goes to 5/2, no matter what the c is. Okay, so that's a good thing to know. In fact, some of the homework problems will rely on you knowing that, so that's why I wanted to go through it. Okay, let's take a look at a. Oh, I just I guess I'm also, if we look at this in general, then if you have y prime equals ay plus b and a is negative, then you know that y of t is going to converge to minus b over a as t goes to infinity. Good, so that's just kind of the general situation. All right, now we're going to look at visualizing a solution. So the general way we look at or we write the first order differential equation is this way, where we have y prime equals some expression in t and y. And so this could be just any expression in t and y. So this is why we write it as f of t and y. And so this actually has some interesting implications. Geometrically, what does this mean? This means that the slope depends on a t and a y. And so in particular, geometrically, if you're in the ty plane and you pick out a particular value of t and a particular value of y, so that you're at a particular point, then you could plug that point into this function and get a number. And so that number would represent the slope of the tangent line of the solution at that number, right? And so I know I'm kind of talking this through. Let's go ahead and write it down. At each point ty in the plane, we can compute the slope of the line tangent to the solution curve by computing this expression at the line at that point. Okay. And so if you do that for all the t and y in the plane, you get what's called a direction field or a slope field. Okay. If the function y is well behaved, the tangent line should be a good approximation to y. Do you remember what the vocabulary word was that we used in calculus? We don't really have well behaved in calculus, right? If the tangent line is a good approximation to y, then y is going to be said to be differentiable. So, yeah, good. Okay. So, definition: a direction field is a plot in the ty plane that gives the local tangent lines to the solution to a first order differential equation, which is really nice. Mainly because you can just look at the direction field and find out all the information you need to know about your solution geometrically. So even if you can't solve the problem, if you can't solve your differential equation algebraically, you can still get a lot of information from the graph. Good. All right. So here's a couple of important points about the direction field. So the arrows represent a small tangent line approximations to the solution. You know what? Maybe I'll pause here and let's go to the online plotter. So if you go to our class website, you'll see the link to the online direction field plotter here. And so here is where you're going to type in, I don't know if you can see this in the video, right in this box is where you're going to type in the differential equation. So this is already a sample. Here we have y prime equals sine of y times cosine of t. Now this would be a really difficult, well, it would be difficult to algebraically solve this. But let's go ahead and just graph the direction field and see if we can get some information from that. So here's the direction field. And so what you're looking at here is each of these line segments represents the slope, right? Slope of the solution. And so what's nice is that using this graph, if I pick an initial point anywhere in the plane, it will plot the progression of the solution through time. So for example, if I start at this point right here, you can see the solution is going that way. And if I start down here, it's going that way. And if I start here, is there a constant solution somewhere in there? It looks like there is. I think there is one at 0 as well, right? So you can kind of see all the different solution curves that you get. And so even though this might be a difficult differential equation to actually solve algebraically, we can solve this graphically pretty easily. One thing I am noticing as I read this, this actually should be dy over dt equals f of ty, since our dy over dt is an expression in y and t. So don't put your expression in terms of x. I'm surprised that is still an issue. Okay, so that is our direction field plotter. So you can just press the refresh button if you want to start over again. Okay, so let's see what we saw. Let's summarize some of the things that we saw in the direction field. So the arrows that we saw are small tangent line approximations to the solution. Any solution curve must be consistent with those arrows. So let me go back to that really quick just to show you what I mean. If I graph the direction field, then could a line like this be a solution to the differential equation? It could not, right? Because the arrows would not be consistent with the direction of your curve. And so that's what I mean by the solution curve must be consistent with the arrows. Okay, and curves where y prime are constant are called isoclines, and they can help you draw a quick direction field. So we're going to do that in just a second. But before we do that, I should say that isoclines are generally not solution curves. So isoclines are curves where the derivative is constant, and they are generally not solution curves. Isoclines just help you draw the direction field. Good. Let's do an example. T minus y squared. What would the 0 isocline look like? Well, to solve that, you would replace y prime by 0 and see what function you get. So if I replace y prime by 0, I get t minus y squared equals 0, and so that's just y squared equals t. So in the ty plane, what does that represent? That's a sideways parabola, right? Good. Now, what if I change the isocline so that y prime is equal to 1. Then we just put 1 in the place of y prime, solve it. I just brought the 1 over to the other side and the y squared over to the other side, so I get y squared equals t minus 1. What's the relationship between these two curves? Yeah, this one shifts the curve forward by 1 unit. And finally, so you can imagine, right? This is a sideways parabola. This is the sideways parabola shifted 1 unit to the right. And what do you think is going to happen with a negative 2? Did you answer it's shifting to the left by 2 units? If you said that, then you're correct. So let's see what that means. I think I have it here. Here's my direction field with the separate isoclines. So here's the 0 isocline. And what do you notice about the 0 isocline again? If you take the local slope along any point on that curve, the slope is 0. Slope is 0, slope is 0, slope is 0. If I look at y prime equals 1, right, I shifted my parabola forward by 1 unit, and any point on this curve has a little arrow that has a slope of 1, 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 slope of 1. Do you see that? Slope of 1, slope of 1, slope of 1. Good. And then finally at negative 2, that's this curve. Every point on this curve corresponds to having a point having a local slope of negative 2, negative 2, negative 2, negative 2, negative 2, negative 2. Good. So remember, these curves that you're looking at are not solution curves. These are helpful curves to show you what the local slopes are doing. Now if I actually plot the solution curves, it would look something like this. And so you can kind of see you can get a general idea of what the solution curves are doing now. Good. I'm going to pause here for a second because I'm at the 10-minute mark. I will be back with another video in just a moment.